I'll talk about this paper, A Survey of Reasoning with Foundation Models. As you know, reasoning is becoming one of the major topic in foundation models and large language models. How can we improve the reasoning, whether they can do real symbolic reasoning or not, what kind of reasoning they do, all these questions in multimodal domain. So this is becoming very important. This paper is a survey of over 650 papers, and I think they did a very good job. So I'll be going over this paper in this video. And just to remind you, you can download these slides if you want from the link that I'll share in the last at the end of this presentation in the last slide. So let me first talk about the increase in the number of papers that talk about reasoning with large language models over time. So after ChatGPT, we see an exponential increase in the numbers, especially at the end of 2023. There was a big increase in the number of papers that talk about reasoning with large language models. So why reasoning? So reasoning is very important for navigating and solving the problems of real world. We are not only interested in the final outcomes, we are interested in how the model reached those conclusions, and they should be fully explainable and understandable by the human counterpart. It's also a fundamental technology in the progress towards AGI. So again, I'm not claiming we are anywhere close to AGI. It's just the right step in that direction. So that's why there is a lot of interest in reasoning with large language models. And we have also seen that reasoning with large language models can also improve the final outcomes of these models. Why are we talking about reasoning in context of LLMs? Why we were not talking about it so much before these large language models appeared? Because it's arguably one of what they call emergent properties of LLMs. So emergent property is a property that is missing in smaller models, but it appears after a certain threshold. That threshold can be the size of the model, it can be the number of training flops, it can be the quality of data and stuff like that. However, there are some other papers that argue that this is a property of LLM, but this is not an emergent property. It just improves linearly with the size of the model and other training parameters. This paper takes a very broad definition of reasoning, and it classifies into two different categories: formal language reasoning and natural language reasoning. Formal language reasoning is where we care more about the notations. For example, mathematical reasoning, logical reasoning. In natural language, we want reasoning in natural language itself. So for example, in question answer, we want the system to tell us in natural language what it is doing step by step. And then they also define like many reasoning tasks and techniques broadly, and then they go into the detail of each of these categories. So for example, in the left hand side, we can see reasoning tasks. So of course, like there is a lot more focus on some of these domains compared to others. For example, common sense reasoning and mathematical reasoning is very well explored area with LLM. Some of the other are less explored. I'm just talking in context of LLM here. So, but you can broadly see like what kind of areas exist. Of course, embodied reasoning, multimodal reasoning are very interesting areas and upcoming areas. Again, in context of reasoning with LLMs. So I'll talk about these categories in next slide. And on the right hand side, you can see like what are the techniques that people use. There is pre-training, as we understand, fine-tuning, alignment with reinforcement learning, human feedback, and stuff like that. There is also mixture of experts where we have multiple models, and then autonomous agents also. So we'll be discussing these in the next slide. Yeah, so they define reasoning also from different perspective. So for example, cognitive reasoning is very similar to how humans draw conclusions given their understanding of the world. Logical reasoning is a process of step by step thinking. And natural language reasoning is more like reasoning about the common sense and the knowledge that is available to reach some conclusion. So let's understand the different types of reasoning. The most common ones are deduction, abduction, and induction. So deduction is where we are given some facts, we are given some rules, and we want to find new facts. You can see the example to understand it well. So, for example, all swans are white. Daisy is a swan. Okay, and now we can easily find out that Daisy is white. Okay, this is how logical reasoning, logical inference works, and usually we don't make any mistakes here because all the information required for reasoning is given. The next one is induction. In induction, we usually have like various facts and we try to learn new rules. This is how neural networks learn or they work. For example, in the example, Daisy is a swan and white. If the model observes this many times, it will end up learning a rule that probably all swans are white. It can be wrong, but it's given the data, it's the most probable outcome. And then there is abduction. In abduction, you are basically inferring the best possible explanation from the incomplete or limited information. So, for example, given all swans are white, Daisy is white, so it can infer that okay, probably Daisy is a swan. So these are three different kinds of reasoning. So, talking about taxonomies of reasoning tasks, there are various ways to look at reasoning. So, for example, formal reasoning versus informal, as I said. So, informal reasoning is less structured, formal reasoning is very structured, it follows some notation, it can be verified. Informal reasoning cannot be verified very easily. Then there is neural reasoning, symbolic reasoning, neurosymbolic reasoning. This basically is a categorization based on the computational framework they use. Backward reasoning and forward reasoning. Backward reasoning is where we know the goal state and we want to find out how the system reached that goal or that decision. Forward reasoning is where we know the initial state and we know some action and we want to see where the model will go as a final outcome. Then there is single step reasoning versus multi step, which is pretty self explanatory. Then there is deductive reasoning and defeasible reasoning. Deductive reasoning is the normal reasoning deduction, and defeasible reasoning is where there is uncertainty and the information is incomplete. There might be a need to go back a few steps and then traverse a different path of reasoning. So this makes it much more complex. Then there is unimodal reasoning versus multimodal. This is basically talking about different modalities of the data. And there are other forms of reasoning that we'll cover some of them in the coming. As I said, we are not in context of LLM reasoning. We're not always interested in reasoning with proper notations, but here are like few mathematical representation for reasoning. Propositional logic, where we have propositions and we have few operators. Then we have predicate logic. Predicate logic have predicates and then they add quantifiers, existential quantifier and universal quantifier. Then we have set theory, we have graph theory, conditional probabilities, and formal system. I'll not go into the detail of this because it's not super relevant. I just wanted to show you what mathematical representations exist when it comes to reasoning. So someone might want to do very strict notational reasoning with LLM, so he will have to use this kind of representations. Yeah, so here are some examples of foundation models. So I believe you already know many of these names. On the left hand side, GPT-3, GPT-4, Bard, Llama, and others. On the right hand side, you can see some models for multimodal and vision. So these are also multimodal, especially is becoming much more common. This is the taxonomy of reasoning tasks. So in order for the models to perform well, we need to see across different kind of tasks. Some models might perform good on, for example, math, arithmetic problem, but it may not perform very well on other kind of, for example, common sense reasoning task. So I believe that the top few, like top 4 or 5, are the most explored areas, like question answers, physical, spatial, and arithmetic. I believe are the most explored area when it comes to reasoning with large language models. So let's look at the common sense reasoning with foundation models. So common sense means that we ask some question answers, and the model can need to know how the world works. Okay. For example, like there is a paper called the reversal curse of LLMs. So LLMs sometimes can answer in one direction, but they cannot go back in the other direction. For example, if you ask who is the Tom Cruise's mother, most of the models will say the name Mary Lee, and but when you ask like who is Mary Lee's son, the models get confused. Okay, so this kind of common sense reasoning is very important for the systems to work similar to humans. Then comes physical common sense reasoning. This is where it needs to understand different physics concept, like concept of gravity, concept of friction, and so on. So here there is a paper that talks about how to use large language models, and what they do is that they do some simulation. They find like pivot events from that. They convert it into tabular form, and then they convert it into a uh, through a network. They convert it into a text, and then they reason on the text itself. Then there is like other kinds of reasoning where we have like objects moving around in the scene. There is a data set paper called Cleverer. um, Here like objects are moving, and you can ask questions about what will happen if this object do this, or again it needs to understand how things work in the world. And then there is spatial common sense reasoning, where you can ask like the model should be able to answer, like for example, which object is in front of which other object, what is the smallest object in the scene, and so on. Then there is mathematical reasoning. Mathematical reasoning distinguish itself from pure natural language reasoning is because it's structured. Okay. um, Sometimes people also use like external tools like calculator and um, some other tools to solve these problems, so it needs to follow some mathematical syntax. Among mathematical reasoning, the most common problems that large language model try to solve are arithmetic reasoning problems, and they are mostly given in the form of math word problems. And while these problems seems fairly easy to even elementary school student, large language models sometimes do struggle to solve these problems. They are becoming definitely much better at it from, let's suppose, a year or two ago. Matt Shepard is one of the paper that is discussed here that has the state of the art in GSM 8K and math dataset, which are the most famous datasets. And basically, the two methods that they use is, one is verification, where they utilize re-ranking multiple outputs by LLMs, and they are also using reinforcement learning with step-by-step PPO to solve these problems much better than others. So geometric reasoning is another area under mathematical reasoning, where we are interested in finding different solutions or proofs of geometric problems. Geoformer is either state of the art or pretty close to state of the art approach that does both the calculation and proving concurrently or in the same model. They call it unified geometric transformer, and they showed that having a unified model can improve the results in both dimensions, calculation and proving. Automated theorem proving is another very important area that is used for hardware and software verification in critical applications. A famous example is in 1994, Intel lost $500 million because of a mistake in the floating point part of the processor, a Pentium processor. Traditionally, humans do it manually or they use some tools to do it, but automated theorem proving is becoming more common, and it can potentially make a big revolution in the field. This is an example from a paper that solves a problem with informal proof and sub-goal based proof. And this is part of automated theorem proving. Sub-goal based proof simply means that they break down the problem into smaller problems and they solve one smaller problem at a time. And of course, the model can decide to break the problem even further and solve it, and then go to the next step. So, scientific reasoning is reasoning in various branches of science like physics, chemistry, quantum. So, just to give you an example, in chemistry, there is a lot of interest in finding new, more friendly, eco friendly materials with different properties, using all the knowledge that was acquired in the papers and other places over decades. Logical reasoning is another very important branch of reasoning. This is actually, you can say, the original reasoning framework that reasoners use, the conventional reasoners use. In this, we want the large language model to reason with the proper notations, and the reasoning outcome is verifiable. We can use some other verification tools to verify if the model did well or not. Mostly the notation used are either propositional logic or predicate or first order logic. You can see some differences given in the table above. Predicate logic is much more powerful compared to the propositional logic, but at the same time it can add some more complexity, especially the quantifiers, existential and universal quantifier can add more complexity. The two ways people use to solve these problems are in context learning or fine tuning. So in context learning, as you know, we just give few examples. So we just show few examples of solving problems using the proper notation, and we expect the model to understand and learn that to solve the problem that we want it to solve. In fine tuning, we fine tune the model to become better at solving what we want it to do. This is an extremely important area, and there is a lot more research that needs to be done in this area. And this is especially important for verification of logical reasoning, verifiable logical reasoning in computer science and mathematics. Then there is causal reasoning. Causal reasoning tries to find the cause and the effect. There are different categories inside also. There are, for example, like in A, you can see like if education is related to the wage. In number B, you can see what should be the weight of different kind of actions or variables on the outcome or outcome event or outcome action. In the third one, you want to find like really what's the main reason for something. And number D is to judge whether something has an effect on the outcome or not. Counterfactual reasoning is also very interesting. In counterfactual reasoning, we make some kind of facts that are not there in the real world. For example, if all cats were vegetarians, what would happen? Like maybe cats would love to eat cabbage and stuff like that. Counterfactual reasoning can be very interesting for some of the things that we want to do with large language models. For example, if we are training a large language model that needs to reply grounded in a document, We can use counterfactual reasoning to see if the language model is actually replying from the document or is it making the stuff up. And these models are trained with a lot of data on counterfactual reasoning because um, just like most of the kids' stories, they are counterfactual reasoning. Animals driving a car, animals going to school, and stuff like that. All that comes under counterfactual reasoning. Uh, then there is visual reasoning. In visual reasoning, we have the perception part, we have the action part, we have reasoning part, and we have like grounding part, like we want to ground it to something. So these are all are very interesting, and there are 3D reasoning also, where we go to 3D point cloud for reasoning applications. These are also being developed right now. Of course, there is much more interest in textual reasoning or math reasoning right now, but I believe visual reasoning will become one of the most important areas of research very soon. So as the models become multimodal, audio reasoning will also become possible, where the models are able to reason based on the audio inputs. And for multimodal reasoning, we saw like here there are many examples of different models that are doing, for example, image text alignment, image text generation, multimodal to text generation, multimodal understanding, and some other commonly used methods. So as I said, so multimodal reasoning is where the next wave will be. Reasoning agents is also a very important piece of puzzle when we talk about reasoning with large language models. These agents are kind of autonomous in some sense, and they can do perception, they can do action, and they can interact, basically get feedback from the environment, and solve some tasks, do some problem in the real environment. It can be a digital environment, it can be actual physical world, and they need to reason, they need to understand the world, and they need to reason about it. They can do many kind of tasks, like they can generate code if required, answer to some questions, and provide some recommendation, and so on and so forth. They can use a vast amount of knowledge that is available, and the skills, reasoning skills they have acquired. They can use external information sources also, in different ways. Uh, the most important differentiation in agents can be single agent versus multiple agent. In multiple agent, they want to talk, the agent might collaborate with each other, or they might compete with each other. They need to have a kind of theory of mind where they understand what other agents can do or will do in the next step. Embodied reasoning is very important when we talk about agent reasoning. So there is a theory that we learn a lot by interacting with the environment through sensory motor skills. So just by interacting with the environment, we learn the concept of what is up, what is down, what is gravity, and things like that. Also, for agents, there are two types of agents: introspective reasoning agents and extrospective reasoning agents. Introspective agents are that execute some action in the environment, but they don't get any feedback. Extrospective agents are that can execute something they can change the environment around them, but they do get a feedback, and they try to either make themselves better or decide the next action based on the feedback that they receive. Reasoning is also now widely used in autonomous driving. There are work going on using large language models and foundation models for driving. For example, on the right hand side, there is an example where we have like the video, and you can also ask the autonomous driver some questions in natural language. For example, you can ask, why does the vehicle behave in a certain way? And in addition to output the control signals for the car, the large language model can also answer, I'm behaving this way because of this. In this case, it's saying because the road is clear with no obstacles. So that's a very interesting area of research too. Other interesting areas of research and focus are some listed here. For example, theory of mind, as I briefly discussed, theory of mind is where the agent try to guess what the other agent is thinking or what the other player is thinking. Then there are applications of reasoning in many domains like weather forecasting on weather data, medical reasoning, what's the better treatment with the explanation. Then there is bioinformatics reasoning, long chain reasoning, where the problem involves hundreds of steps, not like few steps, but hundreds of steps over a large period of time. And then there is like abstract reasoning. Humans are very good at abstract reasoning to deal with concepts at a abstract level, build a hierarchy. For example, if I plan to leave my house and go to my office, I first make this plan and then I break it into smaller plans. Okay, for going to office, I need to sit in my car and drive. So that's another step. And then in order to go to my car, I need to get up from my seat, grab my bag, grab the keys, and then go to my car. And then how do I get up? So from the chair. So humans are very good at this kind of reasoning. And then there is defeasible reasoning. Defeasible reasoning is where the conclusion can be overturned based on the outcomes that it receives. So it might need to backtrack. The information may not be complete in this case. This is a very interesting area of research also. This paper also talks about a lot of data sets that are available in different kind of domains like common sense, math, text, visual, audio, multimodal. This is very interesting. Then it also talks about in context learning techniques. This is very interesting because usually these are the techniques that have a very low barrier to get someone started. In this, for example, chain of thought is like quite famous. Even zero shot chain of thought, and then multi shot, one shot, and few shot chain of thought. Um, so here we just show few examples, and we expect a few example of step-by-step reasoning, and we expect the model to do the same for the question that we are interested in. In zero shot, we just ask the model to reason and give us step-by-step instructions. So this is very interesting area in itself. This is another area of research where the agents have access to external knowledge bases and skill, and it can retrieve it based on the requirement. We also use the terminology of API augmented large language models for this, where the language model is like more higher level intelligence, and then it can call other tools whenever it's required instead of memorizing everything and retrieving it from its own memory. Okay, so this is very good. Large language models can reason, they show some reasoning capabilities, but there are also many challenges that we must understand. So, for example, first is hallucination, where the models make up facts that are not grounded into the problem that we have, or the document that we have, or the domain that we are trying to solve. Then there is an issue of context length, where the input to the model can only be so big. We cannot have longer than that context window input. Right now, this problem is more or less getting solved. We have like a much longer context, but it's still there. Then multimodal learning. Multimodal learning, we humans usually reason in a lot of different domain like modalities at the same time, and this is a challenge still for the large language model. There is a problem of efficiency and cost. For example, like these models tend to be too computationally intensive. So how to reduce the cost of running these models? So pruning, compression, knowledge distillation, and low rank factorization like LoRa, QLoRa are few methods that they support. Similarly, human preference like do reasoning, but also be ethical, uh, which can be different from people from different background, different demographics. So all that is a challenge. And then multilingual support is another, especially for low resource languages, for um, languages that are not written, just spoken. So all this is a very big challenge, and there is a lot of research topics in this area. So here the paper suggests like some future directions like safety, privacy, interoperability, transparency, fully autonomous language agents. Reasoning for science is a big challenge right now because it usually involves multiple modalities. And then super alignment is a challenge that OpenAI started. Um, uh, Getting towards AGI again. Don't misunderstand me. I'm not saying we are close to AGI, but so still there are like significant challenges on how human reason versus how machine reason, and this is one of the project that is trying to solve that. Thank you for watching this talk. There are many ways to connect with me. Reach out to me on LinkedIn, follow me on Twitter, subscribe to YouTube. If you want to download the slides of this talk or other talks, go to the last link, my GitHub page, and go to talk section. You can download PowerPoint slides and you can use them according to the license given in the repository. Thank you.